Okay. Wait. Okay. Hello. Nice to meet you. My name is Eun-Suk Jeong in Fusion Science in Jeong National University in South Korea. And I'd like to present the SAPS from the introduction to analysis of SAPS for helping your understanding. I want to tell you about appreciating for taking this lecture, and I hope this lecture help you. Okay. Then if you have any questions, please email me by this address. Okay, the first lecture topic is SAPS introduction, which is referred to SAPS, X-ray absorption fine structure. Okay, let me give you the outline of this lecture. So first, some of the example of SAPS analysis will be introduced. As you know, there are many tools to investigate materials such as SAM, TEM, XRD, and FTIR. However, you can understand the unique characteristic of SAPS to examine the materials from these steps. Next, the concept of SAPS will be described in brief for helping your understanding. And then, the history of the SAPS will be described in the course of time, which reveals how the SAPS developed to you. The SAPS is divided into two parts, GANES and EXAFS. The GANES is referred to X-ray absorption near rate structure. Sometimes some of people call GANES to any SAPS referred to near rate SAPS. In this lecture, we use the term of GANES. The GANES is referred to extended X-ray absorption fine structure, which is the part of oscillation SAPS. So the GANES and EXAFS will be introduced respectively. Okay, move on. Why do we use the SAPS? Why do we use the SAPS? Consequently, the SAPS is a powerful tool to examine nanostructures, dilute materials, and amorphous materials. Most people use SAM and TEM images to identify the surface of materials. They are suitable for understanding the surface easily. However, they have the sorry. However, they have the limitation of the resolution to distinguish atomic species. XRD is an common method to demonstrate the crystallography of materials, but it is not adequate to examine the nanostructures, dilute materials, and amorphous materials due to the insufficient scattering sources. Okay, look at this example. This is a cobalt-doped zinc oxide film, which has the dilute magnetic properties because of cobalt. It is important to identify the distribution of cobalt in the films because the cobalt atom plays a role to magnetic properties. However, the amount of cobalt in the film is very tiny, 3, 5, 7, 10%. Normally, we took the same image on the top here and XRD to the right. As you see two figures, SAM and XRD, there is no significant discrepancies between specimens. At the time, we had the SAPS experiments at zinc KHG and cobalt KHG. The GANES in the center here and the XAFS, especially stretches from the XAFS to the right, are presented. The GANES and XAFS at zinc KHG don't have considerable discrepancy between specimens like that, right? Such as XRD and SAM imaging. However, you can see the considerable discrepancy in GANES and XAFS at cobalt KHG, right? So we analyzed XANES and EXAFS at cobalt case and zinc case. Also, we compared with the same image and XRD. So we figured out the distribution of cobalt in the films. As a result, same images and XRD didn't have the crucial evidence for the distribution of cobalt, but the XAFS demonstrated it. Okay, second example is platinum nanoparticles on different supports, silicate, titanium silicate, and zirconia silicate. Right? The red circles indicates the platinum nanoparticles on the TEM image. The amount of platinum in the catalyst is less than 48%. We would like to address the circumstance around the platinum nanoparticles during a redox process at different temperature. It is very harsh to address using the previous tools. Yeah. Here is the Fourier transform the XAFS in helium gas to the left, and the XAFS in the redox process at different temperatures to the right. Here. The peaks in the graphs. Yeah, here and this. The peaks in the graphs are contributed by the atomic pairs around the platinum probed platinums. This is contributed by platinum-platinum pair. This is contributed by platinum-oxygen pairs, like that. The XAFS at platinum SVHs reveals the local properties around the platinum atoms, such as the bond length from here to here bond length and the Viola factor or disorder. Now, even though you don't know the Fourier transform the XAFS, you can notice something happened in the circumstance around the platinum nanoparticles at different temperature and different gas, right? Okay, that time we took in situ gens at different gas, helium, hydrogen, oxygen, and different temperatures from 300 Kelvin to 700 Kelvin for platinum nanoparticles on different supports, like that, at platinum SVHT. The gens of specimens are compared with the platinum foil, right? And one of our specimens with 4 oxygens around the platinums. We already found the oxygen coordination number from XAFS results, and then using the acquainted fit and linear convenience fit, so we found out the correlation between the white line, which is the main peak here, and the number of oxygen around the platinum particles. So we make this graph. Also, we fitted the XAFS data to the model obtained from IPEPID, one of the XAFS analysis software. Look at this table. Table shows the fit result of XAFS near platinum SVHT of platinum silicate at different temperature on the different gases. Right? There are local properties such as the atomic coordination number and the bond length D, the Viola factor sigma square, which includes thermal disorder and static disorder. This is the local properties for each cells, platinum oxygen cell and platinum platinum cell. Okay. We also found the number of oxygen for platinum on the top of platinum nanoparticles, right here, like that, this part, from XANES and EXAFS result, which is the N top. Okay. Through the XAFS and XANES results, we made the model of platinum nanoparticles during redox process, like this. Okay. Okay, next example is the subs of zinc oxide in the aqueous solution. we want to address the zinc oxide formation in the aqueous solution. The zinc oxide nanostructures are synthesized from zinc nitrate and high HMT in the aqueous solution. Until that time, when we demonstrated, nobody addressed the zinc oxide formation from the solution to nanostructure. Some people have identified the zinc oxide formation, but they failed to address the zinc oxide formation in the aqueous solution. I mean the aqueous solution. When you use the previous tools, it is very difficult to detect the structural change in the aqueous solution. So we detected it via the subs, as you see, like that. The jet to the left shows something change from zinc nitrate solution to zinc oxide nanostructures, right? Clearly, the Jens shows to you. The XAFS to the right clearly reveals the structure changes. Okay, right? Okay, look at the black line. The black line on the top of the XAFS is zinc oxide powder, which has a bulk structure. There are two peaks contributed by zinc oxygen pair, the first peak, and zinc pairs, the second peak. Okay, look at the zinc nitrate solution. The zinc nitrate solution has only first peak contributed by zinc oxygen pair. The second peak contributed by zinc pairs starts to appear adding HMT. Alright? The second peak in zinc oxide reveals whether it is crystallized or not, because zinc atoms and oxygen atoms are connected as threads in the zinc oxide structure. So, Fourier transformed XAFS can definitely address the zinc oxide formation. Alright? Okay, this is the nanocomposite materials for the battery system. In the battery system, it is important to identify the structural changes and oxidation states during the charging and discharging. The Jens easily shows the change of the oxidation state. When the edge shifted to high energy, which means the oxidation state increase. Okay. This group also took the XRD, right, and XAFS. As we expect, there is no considerable discrepancy in XRD. And they measured the XAFS, which are the reference samples FEF2 and FEF3, to compare with the samples. From the XAFS, they identify the structural properties during the battery cycle, like that. Okay, until now, I have presented the examples of SAPS analysis. So you can take the reasons why we use the SAPS and how we can apply it to the research. Okay. From now on, I'm going to present the concept of the SAPS. What is the SAPS? Okay. This figure, look at this. This figure shows the normalized total absorption as a function of incident X-ray, which is the SAPS. Okay. When you go to synchrotrons, you take the measurement I naught. Sorry, look at this. This is a sample. The I naught is the intensity of incident X-ray, and I is the intensity of transmission X-ray. So the sample has the thickness with T. So by the mirror, I transmission intensity equals to I naught exponential minus mu T, where mu is the absorption coefficient. Right? So we took the intensity of instant X-ray, and I naught And then we found that total absorption ut. Okay. Okay, the XAFS is divided two parts, GANS and XAFS. Here is GANS and here is XAFS. The main peak in the total absorption is a white line. Okay. Okay, let us see the picture on the bottoms here, which demonstrates the orbital of electron in the atom. Now, I want to explain the principle of the SAPS. When the X-ray goes into the samples, it collides to the electron in the atom. Once the electron gets the energy, it can transit into other empty states. This phenomenon makes the peaks in front of the main edge. Here is we call it the free edge. When the electron get more energy, they can move to continuum state, which forms the edge threshold ionization. As increasing the energy, the electron become the photoelectrons in materials that can move around the neighborhood as shown in this picture. Okay. Now we can consider the electron particles as the electron waves in quantum physics. So the outgoing wave goes to neighboring atoms and backscattered. Outgoing wave and backscattered wave makes the interference wave, which contains the information about structural properties, right? The interference wave affects the scattering X-ray, which is detected Earth. Scattering X-ray, and we detected the scattering X-ray. But the scattering X-ray is affected from interference wave. Okay, that is XAFS on oscillation part of SAPS. Therefore, the XAFS includes the information of structural properties. We can extract the XAFS energy of energy using this formula. Yeah, here is XAFS of energy, and from this formula, the mu is the absorption coefficient, and mu naught is background absorption. Delta mu naught is the edge step of background absorption. To be convenient, we can change the XAFS of energy, XAFS of K, where K is the wave number, and it is transformed into the XAFS of R, like that. The transformed XAFS of R is constructible, understandable to you, right? Now, we have a question. Yeah, I already showed this. The GANS part is here, XAFS part is here, but it's not clear what is the critical energy to separate GANS and XAFS. I didn't tell you, right? So now I'd like to tell you about that. Yeah, right? Okay. To explain the answer of the question, so let us see this schematic. There are absorbing atoms here, and first neighboring atoms here with the d distance. The critical energy is defined as the wave number Kc, Kc 2 pi over d. And the photoelectron gets more energy than Kc. It is XAFS. The photoelectron in the XAFS makes the single scattering because of a high energy, right? Single scattering, like that. So we obtain the information of structural properties. Here is when the photoelectron energy is less than Kc, like this, it is dense. Since the photoelectrons have low energy, they are influenced by the neighborhood, such as symmetry and atomic bond and position. The photoelectron in the GANs makes the multiple scattering like that. Okay, generally the critical wave number is about 3 inverse angstrom. So the x-axis is broken at the range of less than 3 inverse angstrom. Okay, now the history of the XAFS is being described. The X-ray absorption edge is found by de Broglie, who is a brother of de Broglie who found matter wave in quantum physics. In 1920, Frick and Harris detected the first experimental XAFS on mangan, Fe, Cs, and D. From 1920 to 1925, the GANs was reported by some researchers. That time, people tried to explain the GANs using theory of Koshel, but it fails. At the beginning of XAFS, the scientists were confused between XAFS and GANs. The Croin explained the XAFS as a long-range order theory, which is useful for XRD. However, it is not satisfying with the experimental XAFS. Next year, Croin presented a short-range order theory based on the transition matrix element in Fermi-Goldner. That is the theory of the XAFS. Okay. In 1971, Sayers Stern, who is an advisor of my professor, and later showed the XAFS was contributed by photoelectron interference patterns. And they proposed that the XAFS contains the local structural information. That time, the XAFS theory was completed by them. Okay. Even though we know the XAFS theory in 1971, there is still problems regarding that the experimental XAFS contains the GANs regions, right? So I mean, in a realistic system, the signal of XAFS can have the multiple scattering, which is a part of the GANs. In 1971, Lee included the multiple scattering effects in the theory of the XAFS, which is a starting point to GANs calculation, right? From these times, people have focused on the calculation of GANs. In 1980, in 1980, Natori demonstrated the GANs calculation of molecular cluster. And Edward Stone, John Lear also investigated the GANs using the Hartree-Fock method. John Lear calculated the curved wave multiple scattering contribution in 1990, and Jeong presented the general multiple scattering. I'm sorry. All right. Sorry. Okay. John Lear calculated the curved wave multiple scattering contribution in 1990, and Jeong presented general multiple scattering to use complex potential in 1992. In the same time, John Lear showed the high-order scattering was required to cover the multiple scattering. In 1995, Stravinsky enumerated multiple scattering paths and decided the contribution with energy, dependent self-energy, and multiple scattering Viola factors. So that time we can deal with the XAFS beyond the first step, right? In 1998, Akudinov calculated both the GANS and density of states with the Hartree-Fock method and Green function. This code is PEP version more than 7. We will use PEP 6 to be included in IPAP, which doesn't calculate the GANS and density of state. If you want to calculate the GANS and density of state, you need to buy this program. However, I would like to recommend another program. In 2001, Charlie proposed the calculation of GANS based on the finite difference method, which is FDMNES. If we want to calculate the GANS in the first principles, I would like to recommend the FDMNES. It's a free software. Okay. Okay, let me introduce the GANS now. The GANS is composed with 3 parts: pre-H, H, and GANS. I already described those before, alright? These figures I already. Pre-H is performed by transition to empty state, right? And the H is the threshold to transit. I'm sorry. The H is the threshold to transit to continuum state, and then the GANS is the phenomena via the multiple scattering. Okay, multiple scattering threshold like that. The GANS is considerably sensitive to chemical and structural properties. So let me demonstrate the features and what we get from each part. Right? Okay, the first, the pre-H is made by the electron transition to empty bound state. Therefore, it is contributed by local geometry, oxidation state, and bonding characteristics. The H is defined as the ionization threshold to continuum state. It is very sensitive to atomic oxidation state. When the main edge shifts to high energy, the oxidation state is increased. The GANS. The GANS is formed by the multiple scattering resonance of the photoelectrons. It is contributed by the atomic position, distance, bond length, bond angles. Also, the geometric structure. If you can identify the GANS, you can demonstrate the actuation state, geometric structure, atomic structural properties, right? Okay, final step in this lecture is the introduction of XAFS. The XAFS gives us the information of the local structural properties and it is extracted from the XAFS. The XAFS is defined as the formula, as this formula, as I explained before. Let me remind the formula. The XAFS is the total absorptions. The XAFS is the total absorption minus and background and divided into the edge step. Background edge step. Here is the background. Smooth background function obtained from autoback code included in the Athena program. The background function will be decided by the autoback code, a part of IPAP. Later, I will explain how to remove the background in detail. This is very important, alright? Okay. As I explained before, the XAFS of energy is converted to XAFS of K, which is wave number, photoelectron wave number. Okay, K, like that. To amplify the oscillation at high energy, okay, we usually use the weight K. After Fourier transformation, we can get the XAFS of R, which can be understandable to us. Okay. What can be found from the XAFS? The XAFS is made by the scattering X-ray signal from an observing atom, which is affected by the photoelectron interference wave. As you see, the interference wave, right? Yes, you remember? Interference wave contains the information of local structural properties. As a result, we found the local structural properties, such as atomic bond length, coordination number, disorder of bond length, and species of neighboring atoms. Okay. Okay, yeah. Finally, I'd like to show the theory of XAFS. As described in the theory of SAFS, the theory of XAFS was completely presented as this formula. When you learn the XAFS, you have to memorize this formula. Okay. N is the atomic coordination number. Here is the N, and sigma square is the Debye-Waller factor, which includes thermal vibration and static disorder. And Rj is the average distance of J2 shells. Sync action pair, like that. Lambda, get this, the lambda. Lambda is the photoelectron mean free path. And then SO scale. SO scale counts the XAFS difference between with and without the hole. The typical value of SO scale is about 0.9. However, it depends on the specimens. Before you make a data fit, you have to decide the SO scale from the perfect materials. Then epsilon is the electric field direction of the instant X-ray. Okay, I finished the first lecture. Thank you for watching this lecture. I'd like to help you for understanding, and I will meet you again with the SAFS experiment and theory lecture later. I'm planning to give you how to take the SAFS experiment and the derivation of the SAFS formula here from simple ideas. Okay, see you next lecture.